So here are various structures, and I might solve just one of these. This, okay, so I can solve either this one or that one. All right, so let's let's solve this one. Okay. Now, when you apply forces to extended objects, what you need is two conditions for equilibrium. You need sum of the forces to be zero and sum of the torques of these forces to be zero. Okay. When you apply forces to point objects, all you need is this condition for them to be, for it to be equilibrium. Okay. Or even if you are applying a force to an extended object, if all the forces are going through the center of mass, okay, then all you need is this condition. Yeah. You need to apply this condition when, when the forces are not going through the center of mass. Yeah. Okay, so let's say you apply forces like this. Now, for this to be in equilibrium, you need to apply both these conditions, okay? All right, so now what we'll look at is, so you have suspended this object, and of course, you don't want this falling down, okay? So what we're going to do is, what this problem is about is, okay, so we have this weight suspended. It could be a sign at a store and stuff like that. And we are going to find out what is the tension in each of these cables. Okay? How thick a cable you need to use so that this doesn't fall down. Okay? What we'll do is we'll look at this knot. Okay? That's a point object. And here are the three tensions pulling on this knot. Okay? And if you don't want this falling down, you don't want this knot moving. Okay? But this is a point object, so all you need to do is apply the first condition. Consider the first condition, that the sum of the forces need to equal zero. Okay? All right, so now, so here is, for this guy, now just consider the first string, just consider this point. There's the weight of the object, and so the tension T3 is equal to mg. Okay, so T3 equal to mg. And now we'll look at the knot. So here's T1 pulling on this, T2, and there's T3. This angle is 45 degrees. All right, so, and we'll draw our x and y axis like this. All right, so let's look at the x component of the forces. So you see, this guy has, T3 has no x component. This x component is being balanced by that, and this y component of the tension is balancing this. Okay. All right, so T2 cosine 45 minus T1 equal to 0. So T2 is T1 divided by cosine 45. T2 is 40% greater than T1. Okay. Now let's look at the y component. The y component is the y component is balancing T3. T2 sine 45 minus T3 equal to 0. But T3 is equal to mg. So T2 sine 45 equal to T3, which is equal to mg. So T2 is mg divided by sine 45. Okay. And if you compare this, T2 is 1.41 times T1, so T1 is equal to mg. All right, so let me redraw this. T1 was equal to mg, T2 was equal to 1.41 mg, and T3 was equal to mg. So to suspend this object, sign or whatever, here was this cable that had to bear that load. This cable had to bear that load. And here's a cable which had to bear 40 times more the load. So let's say this was your shop front. Why not just suspend the sign like that? It's cheaper. And you don't need as strong a cable. Why did you go do this? Spending more money?
So it's not swinging.
There you go. Okay, so for stability, you did that. Okay. All right, so the point of this problem is you calculate the cables and tension in all the cables, and you make sure that you have a thick enough cable and stuff like that. Okay. And the given configuration is serving some purpose. Okay. All right. All right. A small 1,000 kg SUV has a wheelbase of 3 meters. If 60% of its weight rests on the front wheel, how far behind the front wheel is the wagon's center of mass? Okay, so yeah, this is 3 meters. Yeah. So let's say here's the center of mass, and there's mg. What this is saying is the front wheel is bearing 60% of the center of weight, and this guy is bearing 40% of this weight. And we want to calculate this distance x. Okay. So now there are 3 forces acting on this object. There's the force of gravity, and there's the normal force the ground is exerting. There's the normal force the ground is exerting. Okay. This is an extended object, and this is trivial because the 3 forces acting on this is mg, 0.4 mg, 0.6 mg. They're adding up to 0. That's not giving us any information. So let's apply the torque equation. Okay. All right, so we'll calculate the torque about this point, about the center of mass. Okay. What is this guy trying to do? This force is trying to rotate the SUV counterclockwise. Okay. Or actually, and this guy is rotating it clockwise about that point. Okay. Did you guys understand that? We're calculating the torque about this point. This force is would rotate the SUV counterclockwise. this force would rotate it clockwise. Okay? You could use any two forces. You could calculate, if you wanted to eliminate this force, you could calculate the torque about this point, and this guy is rotating him counterclockwise, this guy is rotating him clockwise. You could calculate it about this point, where this guy is rotating him counterclockwise, this guy is rotating him counterclockwise. Okay? So you could pick to calculate the torque about any point. You could calculate the torque about this point, and then this one would be counterclockwise, counterclockwise, clockwise. Okay? You would have to calculate 3 torques if you calculate it about this point. Okay? About which point would the calculation of torque give you the right answer? I'm sorry?
The center of mass?
No, you could calculate it about any point, you'd get the correct answer. Okay? It's just that if you calculate it about other than these 3 points, then life would be harder. You'd be calculating 3 torques instead of 2 torques. Okay? All right, so let's calculate about center of mass. Okay? So this torque, so we're applying sum of the torques is 0. Okay. This one is a counterclockwise torque, which is positive, so the force is 0.6 mg times x. So 0.6 mg times x. And this is the force, the torque due to this guy is a clockwise torque, which is negative, minus 0.4 mg. And the moment arm for this is, this distance is 3 meters, so 3 minus x meters. Equal to 0. And now you see mg cancels. So what we have is 0.6x minus 1.2 plus 0.4x equal to 0. So x equal to 1.2 meters. Okay, so the center of mass is 1.2 meters behind the front wheel. Okay, and this distance is 2.8 meters. So this is, of course, the engine is in the front end, so that center of gravity is closer to the front wheel. Okay. This problem says a uniform plank rests on a level surface as shown below. The plank has a mass of 30 kgs, which is roughly half your mass. Again, most of you here are 50 to 60, 70 kgs. Okay. And is 6 meters long. Again. How much mass can be placed on its right end before it tips? Okay. So we're going to put a mass on this end and find out what will make it tip. Okay, when it's tipped, so here's a hint, when the board is about to tip, it's making contact with only this force. Okay, so what is happening is this portion is, we're calculating the torques about, this is the mass of the box times gravity, this is the mass of piece 2 times gravity, this is the mass of piece 1 times gravity. Okay, how much does this weigh? It's a uniform block.
30
I'm sorry?
30 kilograms.
The whole thing weighs 30 kilograms. Okay, well actually, we can do the following. So what we'll do is the mass of the whole thing is 30 kilogram mg here, and that is 3 meters. So we can do it this way. Okay. All right. So the weight of the box is providing the clockwise torque, and the weight of the board itself is providing the counterclockwise torque. Okay. So we are applying this equation, okay? And the mass of the block times gravity, that's a clockwise torque, times 1.8 meters, and plus mass of the plank times gravity. And this distance is, that's 4.2 meters, that's 3 meters, so this is 1.2 meters. Go to 0. So the mass of the box you can place is equal to mass of the plank times 1.2 meters divided by 1.8.
I'm sorry.
Okay. Okay, so what this is saying is that if you want to support a heavier box, you need a heavier plank. Yeah. Now, of course, in practice, you don't want heavier and heavier planks. So what do you do if you want to support a heavier box? What do? You just clamp this thing down. You screw it down. All right, so you've seen objects like this, and one of the practical considerations will be you'd want to figure out what is the maximum tension what is the tension this cable is bearing, and you want to make sure that the cable is strong enough. So the uniform boom shown below weighs 700 newtons. Yes, so there's 700 newtons. The object hanging from its end is 400 newtons. The boom is supported by a light cable and by a hinge at the wall. Calculate the tension in the cable. Calculate the tension in the cable and the force on the hinge on the boom. So let's say, what's happening? This boom is being pushed against the wall, and the wall is exerting a reaction force. Okay, so let's say the reaction force is like that. Okay, so if you look at the boom, how many forces are acting on the boom? The tension, this weight, and this reaction force. Okay, and if you want the boom to be at rest, all those forces, the sum of all those forces must be 0, and the sum of all the torques must be 0. Okay. So let's see if we have to use both the equations. Okay. Generally, the torque equation is a good place to start. Okay. Calculate the tension in the cable. So we'll first calculate the tension. Okay. To calculate the tension, what we'll do is we'll calculate the torques about this point. We'll use this equation and calculate the torques about this point. When we calculate the torques about this point, you're eliminating this unknown. You're eliminating this force. And you're calculating the tension, and the other two forces are known. So tension will be the only unknown. All right, so now here is the trick. So we're calculating the torques about this point. For this guy, that is the moment arm. Okay, so let's say L is the length of this boom. For this force, that is the moment arm. Okay. So for this force, the moment arm is L by 2 cosine theta, so cosine 20. And for this guy, it's L cosine 20. Okay, how about the tension? Well, here's a little trick you can do. For the tension, this is the Y component of the tension, and this is the X component of the tension. For the Y component of the tension, the moment arm is that guy. For the x component of the tension, that's the moment arm. Okay? All right. So let's apply this. Torque equal to 0. Okay. So this is the x component of the tension. Okay. This guy is making the boom rotate counterclockwise about that point, clockwise, clockwise, and this guy is also making him rotate counterclockwise. All right, so Ty, the moment arm for Ty is L cosine 20. Plus Tx is also making him rotate counterclockwise. Tx is, the moment arm for Tx is this distance, which is L sine 20. And then the 700 newtons is making him rotate clockwise, so negative 700 newtons times L by 2 cosine 20 minus 400 times L cosine 20. And this should add up to 0. All right, let's calculate Tx and Ty. So I'm going to have to, so that angle is 45 degrees, so tension Tx is T cosine 45, and Ty is also T cosine 45. So, all right, I'm going to copy this. Ty was T and Tx was also T cosine 45. T is the only unknown here. See, L cancels. And you can solve for T. All right, so let me copy this to the next page. So what you get is T times cosine 45 cosine 20 plus, this was T sine 45. This was sine 45. This doesn't matter. Sine and cosine 45 are the same, so All right, so let's do this. This is 750 newtons times cosine 20. So the tension in the cable is about 800 newtons. Okay, so this was 700 plus 400 newtons, and all you had to apply was about 800 newtons. Okay? So of course, in practice, you would make sure that the cable can bear 1200 newtons or something like that, just for safety. Okay? And now we'll calculate these reaction forces. Okay? So this reaction forces is, you can do Rx, this is Rx and Ry. And for the reaction forces, we can use this equation. This is the easier equation to use, and that we can use that. The y components of the forces balance the y components, the x components balance the x components of the forces. Okay? You guys following this? Okay, you have a question?
I'm just thinking real hard.
Okay, all right. So now, let's apply this equation. Okay, so the only two forces are Rx minus Tx is 0. So for the x components, Rx minus Tx equal to 0. So Rx is Tx, which is T times cos Tx was T times this T times cosine 45. So 778 times cosine 45. $550 newtons. And the y components. So Ty, Ry plus Ty equal, and they're balancing minus 700 minus 400. So Ry plus Ty minus 700 minus 400 equal to 0. also 550 Newton. So R is 550 I. Okay, so the reaction force is at 45-degree angle, okay? And the boom is there. So those are the forces. Okay. So have you guys ever tried this? You fill up a water bottle and put it in the freezer, and of course the cap would burst. Okay. Water expands by about 9%. Okay, and so but you can Google this sort of. So they did this in the old days in Italy. Let's say this is a marble block in the mountain, and they want to quarry this mountain. So if you want to break off a slab, you find a crack here, okay, and you pour. Well, you find a crack, put a little wedge, and pour water in there. And at night, when it gets cold, the water will freeze. This will expand and it'll push on this guy, and this block will come off. Okay. All right. So, anyways, so we'll see what kind of forces are exerted. Okay. When water freezes, its volume increases by 9%. What force per unit area is water capable of exerting on a container when it freezes? So you have water in a container, in a sealed container, and it's completely full. And when the water freezes, it'll expand. So there's forces being exerted on the container in that direction. And to keep the water in the container has to apply forces in that direction. Okay? And how much forces need to apply? The volume needs to be decreased by 9%. Okay, so the ice is trying to expand by 9%, and so you got to compress the ice by 9% to keep it inside the container. Okay. So here's the bulk modulus of ice. So this is for ice. Bulk modulus of ice is force divided by area, and delta V by V. So they're asking you what force per unit area do you have to apply? This is what they're asking you. So the force, bulk modulus. And the volume decreases negative 9%, 0.0905. And 9 gigapascals. Giga is 10 to the 9 pascals. Okay, so what we're going to do is I'm going to write it in terms of 10 to the power 5 pascals. Yeah. And then 9 times 10 to the 4 times this. So 10, 900 times 9.05. The force per unit area is that. Why did I write like this? Does this ring a bell? This is 1 atmosphere. So the force you need to apply is 8,000 atmospheres. That's enormous. So this in PSI, this would be 15 PSI, 15 pounds per square inch. 15 times 8,000, so let's do that. 15 times 8,000 is 12,000 pounds per square inch. So you freeze water to maintain the size of the container, you'd have to apply a force of 15,000 pounds per square inch. 15,000, well, 12,000 pounds. 12,000 pounds is 4 SUVs. Okay, so the forces are enormous. All right. We'll do 2 more problems here. Okay. A disc between vertebrae in the spine is subjected to a shearing force of 600 newtons. So when you bend forward and lift heavy stuff, the disc between your spines experience shearing forces. Okay? And of course, you don't want any damage to those discs, so you want it to behave elastically. Okay, so here's the disc. And shearing forces are like that. So I will draw 2 diagrams. So now the shearing forces are like this. Okay, disc between vertebrae in the spine is subject to a shearing force of 600 newtons. This force is 600 newtons is almost your weight. Okay. So that's the thing. Find its shear deformation using the shear modulus of that. The disc is equivalent to a solid cylinder 0.7 centimeters high. So that's how high this disc is. And 4 centimeters in diameter. Yeah, so this is 4 centimeters. Okay, a little less than 2 inches. So 4 centimeters. That's the diameter of the disc. All right. So find the shear deformation. The shear deformation is this guy. So when this kind of force is applied, this is how the disc deforms. This is delta x and this is h. Okay. So shear modulus is force over area divided by delta x over h. So delta x over h is force over area. Radius is 2 centimeters. and that's the conversion factor to meters. Okay. And so let's take care of powers of 10. This is 10 to the minus 4. That gives you 10 to the 5. 2 of those cancel, so you get total of 10 minus 3 on top. 10 minus 3. And see this, what are the dimensions of this? This is dimensionless. This is just a number. Okay? So this is 6 divided by pi into 4. Okay, so this is 1 part in 1,000. Okay, so half a part in 1,000. So 0.05%. Yeah, so that's what this amounts to. That's how much your disk deforms. And hopefully when the stress goes away, it goes back to its original shape. Yeah. All right, let's do one more problem. Okay, so this is the suspender rod of a suspension bridge. So what we're talking about is these rods, okay, on the bridge. A suspender rod of a suspension bridge is 25 meters long. 25 meters long is a little longer than the width of this room. Yeah. If the rod is made of steel, what must its diameter be so that it does not stretch more than 1 centimeter when 2.5 times 10 to the 4 kg truck passes by it? So this is a large semi, assuming the rod supports all the weight, I guess. So essentially, you're bearing the weight of the semi, okay? So the Young's modulus, okay, so it's made of steel. Okay. So Young's modulus for steel is, you already saw that, 20 times 10 to the 10 pascals. So what we're trying to find is the diameter. Yeah, so we'll find the radius. So this is the radius. So it's a circular cross section. And force is mg. Y is 20 times 10 to the 10 pascals. And delta L is, you want a stretch of 1 centimeter. So delta L is 1 centimeter. 1 centimeter is 10 minus 2 meters divided by 25 meters. Okay, I'm going to take care of powers of 10 first. This is, so you get 10 to the 6, 10 to the 4, okay. 10 to the 4, and I'll bring the 10 to the 4 up there. So R square is 10 to the minus 4, and this will be in meter square. And that's good because that will give you centimeter square. Okay. And the rest of the stuff is 2.5 times 9.8 and in the denominator pi 20 divided by 25. All right, so so the radius of that cable is 3.1 centimeter, about 1 inch. So that's how thick the cable is. All right, guys. So